All right, let's dive right in. Today, we are tackling a concept that is absolutely fundamental if you're serious about writing Python code, big O notation. If you want to write code that doesn't just work, but works efficiently, especially when things get big, you're in exactly the right place.
So let's kick things off with a scenario. I'm pretty sure we've all been here. You write some code, it runs like a dream on your laptop with your little test data set. But the second you push it to the server and it meets real-world data, it slows to a crawl, or worse, just completely crashes. What is going on?
Well, the answer comes down to this one simple but incredibly powerful idea. It's not really about the raw speed of your code in a vacuum. The real question, the one that actually matters, is how your code behaves as the amount of data grows. It is all about scale.
And if we're going to talk about scaling, we need a shared language, right? For programmers, that language is big O notation. It's pretty much the universal standard for discussing how algorithms are going to hold up under pressure.
So what is it really? Well, the formal definition is that big O describes how the runtime, or the number of operations, grows as the input size, which we call n, gets bigger. We're not using a stopwatch to measure seconds here. We're measuring the relationship between the size of the input and the effort required.
Let's make that a little more concrete. A great way to think of it is like this. Big O tells you how your algorithm is going to handle its growth spurt, as it gets more and more data to process. Is it going to grow up gracefully, or is it going to get all slow and clumsy? And here is a super important point to remember. Big O is almost always talking about the worst case scenario. It's not about how fast your code could be on a good day with a perfect data set. No, it's about preparing you for the toughest situation your code will face, making sure it won't crumble when it matters most.
Okay, so to really get a handle on this, let's picture a ladder. We'll call it the complexity ladder. We're going to start at the very bottom on the most efficient rungs and slowly climb our way up to the ones that we really need to be careful with. Our very first rung, the bottom of the ladder, is the holy grail of efficiency, O of 1, or constant time. This is the dream. It means your code takes the same amount of time to run no matter how big the input is. 10 items, 10 million items, it doesn't care. The effort is constant.
And here's a perfect, simple example. This Python function just gets the first element from a list. Think about it. Python knows exactly where the beginning of that list is in memory, so it just grabs it. The length of the list is totally irrelevant. That's a 1 in a nutshell.
All right, let's take one step up the ladder to O of n, or linear time. This is super common and pretty intuitive. Here, the runtime grows in direct, predictable proportion to the size of your input. So if you double the amount of data, you can expect it to take roughly double the time. It's a straight line.
A classic case for this is finding the largest number in a list that isn't sorted. To be absolutely sure you've found the max, what do you have to do? You've got no choice but to look at every single element. That for loop is your big clue. More elements means more work, 1 to 1.
Now we're getting to something really powerful. Rung 3 is O of log n, or logarithmic time. This is a massive leap in efficiency. With logarithmic algorithms, every time you double the input size, you only add about 1 extra step of work. Just 1. Compare that to linear, where doubling the data doubles the work. This is fantastic.
The poster child for O of log n is, without a doubt, binary search. Now, the catch is your data has to be sorted. But instead of checking every item, you jump to the middle. If that's not what you're looking for, you instantly rule out half of the entire list. You just keep cutting the problem in half, over and over again. It's incredibly fast on big data sets.
Okay, let's just take a quick pause here. This table gives us a great visual recap of the rungs on our ladder. You can really see how the growth rates start to diverge. We've climbed up from the super fast O1 and O log n through the very common ON, and you can see what's coming next. So now we're climbing higher up the ladder, and frankly, it's getting a little dangerous up here. Welcome to ON squared, or quadratic time. This is where the performance of your algorithm can just fall off a cliff if you're not careful. The runtime grows by the square of the input size. The classic sign, the thing you should always be looking for, is a loop inside another loop, where both are iterating over the same data. For every single item I in our list, we have to go through the entire list a second time with j. The workload doesn't just grow, it explodes. And to put a number on that explosion, if your list has just 1,000 items, which isn't very big, this innocent-looking code will perform 1 million operations. If the list has 10,000 items, that's 100 million operations. This is how servers crash. Okay, so we've climbed the theoretical ladder. Now for the most important part. How do we actually apply this knowledge in our day-to-day Python coding? Let's build a practical toolkit. This right here, this is gold. It's a cheat sheet for the big O of common operations on Python's built-in data structures. And I want you to pay very close attention to dictionaries and sets. If you need to check if an item exists in a list, you might have to look at everything. That's O of n. But in a dictionary or a set, it's O of 1, constant time. That is a game-changing difference.
So how do you start figuring out the big O of your own code? It's actually a pretty straightforward process. First, just look for loops. They're usually the most dominant part of your algorithm. A single loop often means O of n. Nested loops often mean O of n squared. Next, check the docs for any built-in functions you're using to see their complexity. And finally, remember, we're looking at the big picture, so we ignore constants. O of 2n just simplifies to O of n.
Which brings us to our final step, and honestly, the whole point of this. Understanding Big O isn't just about memorizing some formulas to pass an interview, it's about fundamentally changing how you approach writing code. It's about developing a scalability mindset. So, let's nail down the key takeaways. 1. Always remember that Big O is about how your code scales, not its raw speed on a small data set. 2. Learn to spot the dominant parts of your code, usually the loops, because that's what will control the performance. And 3. Know your tools. Leveraging Python's built-ins, especially the O1 nature of dicts and sets, is like a developer's superpower.
And so I'll leave you with a challenge. Go look at your own code, one of your own projects. With this knowledge fresh in your mind, I want you to ask yourself, what's the biggest performance bottleneck you can find? And now that you understand the latter, how could you refactor it to be more efficient? Thanks for tuning in.